Next, we're going to take a look at the compound interest model. So rather than creating a table and having to go every single quarter to calculate how much money is in the account, we are going to have a model that we can just use to say how many years have gone by, how often are we compounding, and we can figure out how much is going to be waiting for us at the very, very end. So this model is a formula of sorts that you can just use to plug in all this information and figure out what we're going to have at the very, very end. So this model is based off of the exponential model we looked at last week. We looked at y was equal to a times the quantity of 1 plus r raised to the x power. A was kind of the amount you started with. X up here in your exponent was the time, the number of years that went by, and then the r in there was your percentage rate. Each year, how much were you increasing by? What percentage rate was that going to be? Or each year, how much were you going to decrease by? We talked about how R could be a negative rate as well, which meant that you were going to deal with a decay situation, and we had a number that was less than 1 overall. The compound interest model is set up the same way, but it adds in one new number for us to use, and that is the number n. So if you look, the very first spot where n shows up is right in here. We have r being divided by n. That's what we did when we took the 20% and split it up over 4 times in the year. That n is the number 4, how many times we're compounding. So we took 20% divided by 4, and we ended up with 5% overall. So what's going to happen with your compound interest model is that you're going to have your rate that happens over the course of the year, and n describes how many times we're going to split, how many pieces we're going to divide that rate into. The other spot where you're going to find the n is up here in the exponent, n times x. And this is because we are compounding it several times in the year. So when we compounded quarterly, we had 4 different times that we needed to add that interest into the total amount. So we had to do 4 times that 1 year that went by. If you think about the whole table we did for situation 2, there were 8 different boxes for us to fill in, or 8 different rows for us to calculate the interest and add it into the total. So that would be your n would be 4 times in the year, x would be 2 years. That's the total of 8 times that we had in there. So it's the only change that we're going to make to the exponential model. Everything else is going to be the same. So what does that mean for us? The a that's in there is still the initial amount, your starting amount, or how much money you're going to put into this account or possibly borrow from somebody. The r is still going to be your percent rate, and this is going to be for 1 whole year. Over the course of the year, what is your annual percentage rate, your APR, that you're going to be looking at? N over here is going to stand for the number of times compounded in 1 year. We're going to take a look at a couple of the different adjectives that you might see in a word problem to let you know what number this is supposed to be. X, as it was before, still stands for the time, and in this case, we're talking about the number of years that pass. And lastly, the y is kind of your end result. It's the ending amount of money waiting for you at that after all of those years have passed. So a lot of this information is still the same as before. We're just kind of adding in that extra n, talking about your compounding. So what number is n? How do we use that? We're going to look at the same situation, and we're going to look at how it compounds over different or how the money accumulates over different types of compounding. So here's our situation. We're putting $1,000 into an account. I'm going to highlight that 1,000 into a savings account that gives you 6% annual interest. How much money will be waiting for you at the end of 4 years if you compound? And here we have 6 different types of compounding to work with. So before we get into the compounding, let's just kind of identify the parts that we do know based on the different variables that we have in our formula. So we need to scroll up a little bit. Okay, so the $1,000 is what we're putting in there. What variable or what part of our formula represents our starting amount? In this case, that is the variable a. A is that starting amount, that coefficient that we have right in front. We see our 6% annual interest. That is standing for your R. Now what we're going to do is we're going to change that into a decimal, so that's going to be 0.06. The next number we have is the 4 years. If you're talking about the total number of years that's going to go by, that's going to be in the X spot. Now, what's going to change in each one of these, all that information is going to be the same no matter what we do for this box in here. What's going to be different is what is the value of n. If we compound annually or you compound yearly, it's talking about how this is only going to happen once. N is going to be a total of 1. So in here, I'm going to insert what this function looks like. I'm going to insert an equation. I'm going to hide that again. And in my equation, I'm going to say y is going to be equal to 1,000 times 1 plus. I'm going to put in a fraction. If you're using the equation, the fraction comes up with these boxes. And is the very first option A over B. And it kind of creates 2 little spaces for you. We're going to do the R value, 0.06, and divide it by the 1 of our n. And that's going to be raised to the 1 times a 4. So that's what it looks like when you set up your formula. If you're going to type this into your calculator, if you have a graphing calculator, you can type it all in at once, and this is how you would do that. The 1,000 parentheses 1 plus 0.06 divided by 1, close that parentheses, raise your exponent with the caret symbol, and when you do your exponent, make sure you do a parentheses around the 2 numbers in your exponent. 1 times a 4. Then we hit enter, and it's going to tell me that I'm going to end up with a total of $1,262.47. I'm going to round down. When you use the Delta Math program, it may ask you just to round to the nearest cent, and in this case, you may round up. So that's something to check if they tell you your answer is incorrect the first time. Maybe round it the other way. So this is your formula. And this is the total amount we'll have at the end of our year. We started with $1,000. If we compound it just once at the end of the year, we're going to end up with a little over $1,250. So we gained about $262. So semi-annually means kind of when you think about like the semi-annual sale, it means it happens twice in a year. So this is the case where the n value is going to change into a 2. So when I insert my new equation, it's going to look like y is equal to 1,000 times 1 plus, we're going to have a fraction, our 6%, 0.06 divided by 2 this time, raised to the 2 times the 4 years we're going to let this sit for. So my calculator, I'm going to do the same thing, 1,000 times 1 plus 0.06 divided by 2, raised to the, and of course in the exponent spot, you want to do 2 times a 4. And this time we're going to end up with a total of $1,266.77. Now quarterly, we've already done, but it refers to the fact that n is going to be 4. You're going to break up your rate into 4 different times. So I'm actually just going to copy this formula in here, and I'm going to change the 4 around. So the 0.06 is still the same rate. I'm going to divide it by 4 this time, and in my exponent, I'm going to end up with 4 times 4. Now, if you're somebody who doesn't have the graphing calculator available to you, you just have a scientific calculator, here's one of the ways you might want to type in this into your calculator. You'll do the 0.06 divided by the 4 first, add a 1, raise it to the 16th power, and then multiply it by the 1,000. Again, it depends on the type of calculator that you have. Monthly refers to the fact that there's 12 months in the year, so in this case, n would be 12. So everything about this formula is going to be the same, except we're going to change that bottom number into a 12. So we're going to delete that 2. I'm going to type in 12 Up here in my exponent, it will be 12 times 4. So 1,000 times the quantity of 1 plus the 6% divided up 12 times in the year, raised to the 12 times 4 years. Because the 12 in your exponent is the number of times in a year, and then we're letting this run for 4 years. So it's a total of 48 times that we're going to do this compounding. We have our final result. We're going to have a total of 12, 70, 80, or 48. Now, weekly, you have to think about how many weeks there are in the year. On average, there are 52 weeks in the year. So we're going to do that same thing. We're going to take that formula, and instead of that end value, we're going to make it a 52. Up in your exponent, it'll be 52 times the 4 years. What I'm going to do in here is I'm just going to change that 12 into a 52. We're going to end up with a 1271.07. The last one is daily. For this exercise, we're going to ignore the fact that there are leap years and that we sometimes get an extra day, and we're going to treat this as 365 days in the year. And we're just going to say it's going to be 365 all the time. So in that case, we're going to change our end value here in the denominator to 365, and up here in the exponent, also change that to 365. So 365 and 365 times 4 years. We're going to let this run. And we have 1271.22. So we take a look at all the different amounts that we ended up with. So we started with the same amount of money of $1,000. We start with the same percent of 6%. We're still going for 4 years. But how we compound it actually changes the amount of money we're going to end up with. If we compound it just annually, just once, 6% at the end of the year, at the end of each of the 4 years, we're going to end up with 1262. And then if you kind of look at what our final results are, 1262, 1266, so a little bit more, 1268, so we're going up even a little bit more, 1270, all the way to daily with 1271. So we gain almost a full $10, well, not quite, but almost $10 just by compounding this daily instead of compounding it once at the end of the year. Why do you think that is? Why do you think we end up with more money at the end of the year? And the question is, if I keep compounding it, let's say we compound it every second of every day, why won't I get an infinite amount of money? Why doesn't this go up by more? So the first, from annually to semi-annually, we went up by about $4. And then we go up by maybe about another $2 and some change. And then after that, we go up by a little bit less than $2, and then we're only going up by less than $1, and then even less than that, we only go up by a couple cents at the very last change. So if I'm going from like 52 times to 365 times of compounding, I didn't really go up by that much between these two amounts. So why do you think that is? Why do you think that this isn't going up a much? That's what your first question is going to be. Why do you think that the compounding daily doesn't give you that much more money over the compounding weekly? Pause the video and try to think about that. We're going to go through one example together of how we're going to take this information and just do one iteration instead of all 6 that we did up in on the box up there. So here's some of the sample problems you're going to have to work through, okay? When my daughter was born, I invested $250 into a college savings account. The account has a 5.2% interest rate that's compounded monthly. How much will be waiting for my daughter when she turns 18? So we put that $250 away, and we're just going to let it sit there. We're not going to take any money out. We're just going to let it grow. So what we're going to do is start with all of the numbers. The first number is 250. That is how much we're starting with. That's going to be your A value. The account has a 5.2% interest rate, so that's the R, and we're going to change that into a decimal, so that would be 0.052 is 5.2%. It has the key phrase compounded monthly. That lets me know that N is going to be 12 months in the year. How much money will be waiting for her at the end of 18 years? That is my X value. That's how much money we're going to be waiting for, or seeing how much is at the end. So I'm going to insert a new equation. I'm going to say Y will be equal to, I'm starting with $250. We're going to add to that the rate of 0.052, and it will be divided up 12 times because we're compounding monthly. And we're going to raise this to an exponent that would be 12 times your 18. So that's the overall setup. That's what I want to see from each one of you, is how is that formula set up and where are all those numbers plugged in. The next thing we're going to do is just go to the calculator and figure out how much this is. So 250 times the quantity of 1 plus 0.052% divided up 12 times, raised to the 12 times 18. And make sure that 12 times 18 is in parentheses. You want to make sure that that's in there. And then we're going to hit enter, and it looks like at the end of those 18 years, she will have $636.15 waiting for her. Now that may not seem like a whole lot of money, but if you think about it, I started with 250. I only put 250 in there, and it more than doubled in the course of the 18 years. I didn't have to do any work. I just let it sit there, and I more than doubled my money. This is kind of what the benefit of some savings accounts and some savings bonds will do for you, is that if you have those and you can make that initial investment and leave it alone, it can produce a lot more money for you in the long run. What you're going to do next is the 2 practice problems down here where you're going to have your bank account in 2 different scenarios, and you want to calculate how much money is waiting for you at the end. What I'm looking for you in your work is something similar. Let's highlight this. Something similar to what I typed in right here is what I want you to be doing for these practice problems, is showing me how the formula gets set up as best as you can, and then show me how much money is there at the end.